in the first lecture, we started by going over the electric force and how it worked. So we can have a look here, and basic concepts of how different objects with different electric charges interacted. So we can see all that here. We talked about friction. We talked about specific interactions between them. Then we talked about the atom and some of its properties, as well as how atoms interact at an atomic scale when it came to the electric force. Then we pretty much quantified the electric force. We talked about how we could calculate it, how we could understand its direction, and whether or not it would be moving towards or away from other charges, and why that would happen. And then we talked about all of the things that the force depends on, so the radius, the size of the charge, the constant K, and then we did a few calculations, so we did a few examples here. And then the last class, we talked about the electric field, which we use to explain the electric force. We said that the electric force is just a consequence of the electric field. So the electric force exists because a particle or a charged object has entered the electric field of another charged object. So that is what the electric field is. And then we talked about how to draw the electric field, how to represent its field lines, which are shown in red here. We talked about how to draw them with two of the same charges, two of different charges. And then we talked about what the E field vector represents, which we said is always tangent to the field line. Then we went over how we could compute that, how it's made up of the E field resulting from two different charges at one point, if those two different charges are sort of reasonably nearby, right, before R gets too large and makes it have no impact. We talked about electric field on surfaces, and we just did a bunch of calculations, which are quite similar to the force calculations. They're just we kind of just drop the variable, right, because E is equal to F over Q. All right. So in this class, so class 4, we're going to be going over the motion of charged particles in a uniform electric field. So we're going to sort of we've talked about forces now. We've talked about electric fields. Now we're going to be able to quantify how particles are going to move through electric fields if they themselves have electric charges. So let's go back. So I'll title this section Motion of Charged Particle in a Uniform Electric Field. Okay. So, first of all, we know so far from before, so I guess I could write notes before I begin. First of all, that E is equal to F over Q, or in other words, F is equal to Q times E. So that's just from our previous lecture. We just rearranged the equation to get an equation for the force. We also know from NYA physics or mechanics that the force on an object that is accelerating is equal to the mass multiplied by the acceleration. And then we're going to be using sort of models of constant acceleration for motion in 2D. So I'll write that model that we're going to be using is constant acceleration motion in 2D. So what's happening is that the uniform electric field, right, because we're considering a uniform electric field, not just any electric field, it's going to cause a sort of projectile motion of the charged particle between two plates, which are required for the uniform electric field. So the uniform electric field causes projectile motion between the plates. And then lastly, obviously, I'll write it above. The electric charges that we're going to be considering are either positive or negative. And then these particles are going to follow a parabolic path. And whether that path is concave down or concave up, we don't know yet, but we just know that the path will be parabolic. So, for example, if we shoot let's say we shoot a particle like that, its motion might look like that, which is a parabola, right? If you extend this into a graph, right, you're getting sort of the right section of the parabola that might be this equation, for example. Okay. So, to calculate the motion of a charged particle in a uniform electric field, we use the kinematic equations that we had in mechanics, and we just rewrite them a little bit. So I'll write that down. To calculate the motion of a charged particle in a uniform E field, we use kinematics. So now let's name our kinematic equations, I guess. So kinematics. Okay, so as we did in mechanics or NYA physics, we break down the motion into two components. So on the first hand, there's the x component of the motion, right? And we're considering a scenario where we have a particle. So let's say I'm not going to draw a single one. Let's say I'll just draw two, right? Just to demonstrate that it could be either a positive or a negative charge moving through the electric field. But if the electric field is in, I don't know, say that direction, that's how we're going to look at the scenario. So when I say the x component of the motion, I'm thinking that the x component is the horizontal portion of the motion, and the y component is the vertical component of the motion. So in this case, because the force is equal to q times E, in the x direction, there is no force, right? So the acceleration in the x direction is 0. So we have constant motion. So that simplifies our equations quite a bit in the x direction. So the x component of motion has the following equation. So ax equals 0. And then it can also be said that v naught x, meaning the initial speed in the x direction, is equal to vx, so the speed of the particle in the x direction over time, is constant. I call it some constant C, or I'll just write constant. There you go. And then more specifically, we could write that the motion, so the x value of the particle is equal to its initial speed, or Vx, V naught, whatever you want to call it, multiplied by the time, right? There's no additional acceleration component. Or maybe you could think of it as there being an acceleration component, except that acceleration component is equal to 0. So that's that. And then, of course, we have our same equation here, which is F is equal to QE, which is equal to MAY. And then M, or I'll write this on the other side, actually, because I haven't talked about the Y component. So that's the X component, simple. Now the Y component is slightly more complicated because it's in this direction that the acceleration is happening. So first of all, the speed is no longer constant, right? It's no longer true that V naught Y is equal to Vy, right? Because the speed is increasing over time, right? Because there is an acceleration, there is a force that exists. So we can say that V, let's say Vy, is equal to V naught Y, but plus A of 0 multiplied by T. And then we have our standard mechanics equations. So I'm not going to write this Y every time because it just gets annoying, but V is equal to V naught 0 plus 2A, and then this is just sort of delta Y, or change in height, or delta S, delta H, whatever you want to call it. It's all the same. And then Y is equal to Y0 plus V0 T plus 1 over 2 A T squared. And then there were those equations that I was talking about before. So first of all, the one that I mentioned initially. So F is equal to QE, which is also equal to MA, of course in the Y direction because there's no MAX. And then MAY is equal to plus or minus E multiplied by the E field divided by M. And then we have that Q is just plus or minus E, which is the fundamental charge on an electron, which is 1.6 times 10 to the minus 19 coulombs. All right, so I guess we'll talk about the situation in general. So let's call this electron. Maybe I'll do it in blue. So an electron falling through a uniform field. So first of all, there are two charged plates that exist, and these charged plates are electrical devices that we call capacitors. And we're going to learn about capacitors later, especially in Unit 3, I think. But for now, we just need to know that they're charged. So the situation kind of looks like this. If I were to illustrate it, you have, let's say, some sort of battery, right? Obviously, the drawing of your battery isn't too important, but let's say you have something like that. Then you have a plate above, and you have a plate below. Let's say something like that. Now, we also have that the positive side of the battery, so I'll write that positive side here, negative side here, is connected to the plate, which is obviously positive. And then the negative side of the battery is connected to the negative plate. So this plate is negative. And then the electric field, as we discussed, will run from the positive, the positive charge, all the way to the negative charge, no matter what we're talking about. Even if in this case we're talking about plates and not individual charges as we were before. So we can draw, our field lines. like that. Something like that, maybe a few in the middle. So those are field lines. Now, if we were to consider the force on an electron traveling through this field, what would that look like? Well, as we know, the field lines represent the direction of the force in which a positive particle or a positively charged particle would feel if it were in that E field. So if I place a positively charged particle in the E field, it would feel a force in the direction that the field lines are going in, so in this direction. Now, on the other hand, if I place a negatively charged particle, we know from the previous lecture that it will feel a force moving in the opposite direction of the field lines, that is to say, in this direction. So, if I shoot a particle here with some initial speed, let's say I do it with a positive particle, what's going to happen? Well, as it moves along, it's going to feel zero force in the x direction, so it's just going to continue moving at constant speed. So its trajectory, unaffected, might look like that, which is moving straight ahead, but it will feel a positive, or it will feel a force moving towards the top, as is indicated by the electric field lines, and so it will move like that, slowly. So it will have a constant acceleration, which we quantified just before, in the y direction, and zero acceleration in the x direction. Now, if this were a negative particle, it would do the exact same thing, so it would have a constant speed in the x direction, but it would accelerate in the y direction, but in the other direction, in the direction opposite to the direction of the field lines. So we would have F is equal to this. And then, yeah, that's pretty much it. So also, in general, we're going to be given, when we're calculating these things, we're going to be given how far away these plates are, because it'll help us calculate a bunch of stuff. It'll give us that delta y often that we're going to need, or at least a portion of it. The question might ask, how long will it take before we travel half of the height in between the plates? So you'll need to know what delta y is to determine half of delta y, and then to determine, the t-value in that case. So, let's do an example. So let's call this example 1. Let me just check how I denoted examples. Okay, like that. Got it. So, example 1. An electron with velocity 2.00 times 10 to the 7 meters per second is projected into a uniform electric field between two parallel plates as shown. If the electron enters the field at the top and emerges from the other side, after missing the bottom plate as shown, and then they tell us that the plate is 3 centimeters long and the distance between them is 2.0 centimeters. And the question is to find the maximum, I'll write that actually. So find the maximum electric field between the plates. Let's illustrate it. So we have, first of all, that we have two plates and we enter on one side. And we have the E field, let's say, going upwards. And it's an electron, right? So we're going to know what kind of motion that electron wants to do in this type of field. So if I have an electron and I shoot it, let's say I shoot it like that, its motion will look like that. And it exits just after missing the bottom plate. So what that tells us is that, first of all, it's the distance that it has traveled in the x direction is equal to the length of the plate, which we said is 3 centimeters long. So delta x is 0.03 meters, and then delta y is 2 centimeters, right? Because if it starts at the very top and comes out at the very bottom, well then it must have traveled, or it must have a change in height that is equal to the difference between the plates, which is 2 centimeters, so 0.02 meters. So, first of all, we can calculate the time it took to travel across the plate, right? And the easiest way we could do this is by looking at the x component of the motion, because I know how long it's traveled, and I know, and I'm looking for the time. So if I say, for example, I know the speed as well. So if I look at the x component, so maybe I'll write the x, and I'll write my equation. And sometimes it helps to write the equation, because then you can realize what variables you have and what variables you're missing to solve. So in the x direction, we said that v of x is equal to v naught, but which is also equal to, or we wrote it like this actually. So if we rewrite that, we can solve for t to be equal to x, or I guess delta x, divided by v of x. Now both of these things we know. So 0.03 is how far we traveled in the x direction. V of x is given in the question, which is 2 times 10 to the 7 meters per second. 2.00 times 10 to the 7. So we can calculate this. So it gives us 1.5 times 10 to the minus 9 seconds. So now we can look at our y component. Because remember, our end goal is to find the maximum electric field, right? Which we said before is equal to, let me find the equation, we can calculate it using this equation here, right? These equations. So let's go back. So first of all, y. So in the y direction, if we're talking about the motion, we know that y is equal to y naught how did I write it? Let me just double check. Yeah, but y naught plus v0t plus v0t plus 1 over 2 a t squared. Okay, so first of all, we know that because the electron is moving horizontally initially, it has no initial vertical movement, so that is equal to 0. And then we can move y naught over, so we would get that essentially that the change in y is equal to 1 over 2 a t squared, right? Move this guy over. So then we can solve for our acceleration, which we would need. So delta y, we send the 2 over, times 2. We divide by t squared, which we know now, and this is equal to a. So we can fill in all of our missing data points. So 0.02, which is delta y, as we said at the very beginning, multiplied by 2, divided by t squared, which we just calculated to be 1.5, I believe, times 10 to the minus 9. So we can punch that in, v squared. So that gives us 1.78 times 10 to the 16 meters per second. And then we also know that E, or actually we can derive it from the very beginning. So F is equal to ma, which is also equal to E multiplied by the electric field. So we can solve for E and say that E is equal to ma divided by E. So the mass of an electron is constant, which we know to be 9.11 times 10 to the minus 31 kilograms from our equation sheet. And then we just calculated its acceleration, which is 1.78 times 10 to the 16. And then we can divide by the fundamental charge of an electron, which is 1.6 times 10 to the minus 19. So we can punch that in as well. And that gives us 1.01 times 10 to the 5. And of course, because we just calculated an electric field, the units are newtons per coulomb. So that's how we get to our answer. So we can sort of look at what we did here. So first of all, we realized that we needed to find the electric field, and the electric field depends on the acceleration, as we found in this equation here. So because the acceleration is constant, we can look for that acceleration no matter where we are. But because we knew how long it took us to get to the end of the field, so after we had traveled the length and the height of the plate, we knew how long that took, we knew where we were, so that point was convenient to use. So that's why we used that point. We were able to calculate how long it took us to get there, and then from that, we were able to find the acceleration, and then of course we could plug that in to our equation at the bottom and solve it for the electric field. Okay, so let's do example 2. So an electron enters a region where there exists a uniform electric field with a velocity of 2.00 I plus 3.00 J times 10 to the minus times 10 to the 6 meters per second. They tell us that the electric field in the region is given by E equals 0I plus 200 J newtons per coulomb. So A, determine the acceleration of the electron while in the field. B, if the electron enters the field at point 0, what will be its coordinates? 2.00 times 10 to the 7 seconds after it has entered the field. And then they're asking what will be its velocity at this time. Okay, so for this question, the first thing that we can notice is that the velocity is given to us in a different way than it was before. It's given to us in component form, right, using the unit vectors I and j. So all we know is that it has 3 units in the x direction and 3 units in the y direction, which is actually helpful because, I mean, really there are 3 ways they could give us the speed and electric field, right? They could first tell us that it's just equal to some number in the x direction or just equal to some number in the y direction, which is very convenient, right? It just means it's moving like that or it's moving like that. Very easy to deal with. When they give it to us in this direction, I mean, it's also pretty convenient because we can just, the force or the speed is already broken down for us, right? It's already broken down. We know that it's moving 2 meters initially per second in the 2 meters times 10 to the 6 in the x direction and 3 times 10 to the 6 meters per second in the y direction. So it's not too bad, and the same thing for the electric field. But they could instead give us a speed at an angle, for example. So they could say we're moving 10 meters per second, but I guess it would be much faster. Let's say 10 times 10 to the 6 meters per second at 50 degrees from the horizontal. So that would be something like that, right? And then you'd have to compute the x component by saying 10 times 10 to the 6 cos of 50. That's going to be your x component. But we'll deal with that later. But all that to say that this form is pretty convenient. So, solution. I like to draw them because it helps visualize sort of what we're doing. It's going to help us solve the problem as well. So, first of all, we have our electric field, let's say like that. And then we know that the electric field in the region is given by 200J. So what that means is that the electric field is moving in the positive y direction and in no other direction. So the electric field must be moving vertically like that. And then we know that we send in an electron at 2 meters per second, or 2 times 10 to the 6 in the x, and 3 times 10 to the 6 in the y. So that's going to look something like, let's say like that, right? So it's going to look something like that. Maybe I'll do it in red so it makes a bit more sense. So our initial speed vector, velocity vector, will look something like that. And we're sending in an electron. Now, of course, this is an electron, so it will feel a force downwards. So its motion will look something like that. Right? It's still parabolic, except now it's concave down. So let's calculate the acceleration. So, first of all, we know that the force of the electron is equal to QE. So let's say F is equal to QE. And then we also know that the acceleration, or that I guess I can write force is equal to mass times acceleration. So we can derive that same equation that we used last time. So from last time, QE equals MA, or A is equal to QE divided by M. So QE is, of course, Q is still going to be the fundamental charge of the electron, except now, instead of we're going to have to deal with the negative sign, right? Because the acceleration, and it makes sense, right? Because the electric field is positive, it's 200, the mass is going to be positive, but Q will be negative, and that makes sense because that will give us a negative acceleration, which also makes sense because we can see that the particle was given an initial speed like that, and its final speed is like that. So there has been no change in the vertical speed, in the horizontal speed, but the vertical speed has gone from going straight up to going straight down. Thus, there must be a negative acceleration in the y direction. So Q is going to be minus 1.60 times 10 to the minus 19. E is still 200, as is mentioned in the problem, and then the mass is still the mass of the electron, 9.11 times 10 to the minus 31. And we can compute this from minus 1.6 times 10 to the minus 19 times 200 divided by 9.11 times 10 to the minus 31. And that gives us minus 3.51 times 10 to the 13 meters per second squared. So, and also, this is in the y direction, right? So you could write, I suppose, a y, right? Because the acceleration is moving straight downwards. Okay, so that's A. Now for question B, they're asking, if the electron enters the field at point 0, what will be its coordinates 2 times 10 to the 7 seconds after it has entered the field? Okay, so first of all, they're asking where we're going to be after a certain amount of time. And to deal with questions like that, we can use our equations that tell us the position of the particle over time, right? We have specific equations that help us do that. So in the y direction, we know that x is equal to the initial speed, which does not change over time, multiplied by the time. So, and we know the initial speed in the x direction because it's given. So it's 2.00 times 10 to the 6 meters per second. And then they're asking us after 2 times 10 to the 7 seconds. So we can calculate that pretty easily. It's negative 7 here, actually. Yeah, there you go. That makes more sense. So, which is 0.4. And then in the y direction, we can use our equation, which is y of 0. Oh yeah, I should mention that here you can add x of 0 as well, but we're starting at the point 0, so the coordinates, the initial coordinates are equal to 0. So there's no need to write those, right? Because they're just equal to 0. So here we get vt plus 1 over 2 at squared. So the initial speed in y is given. So it's also 3.00 times 10 to the 6. And then the speed is 2.00 times 10 to the minus 7, or sorry, the time. And then we add up a half times the acceleration, which we just calculated to be minus 3.51 times 10 to the 13. And then the time, of course, same value as before, still given, 10 to the minus 7 squared. Okay, so we can compute this now. Okay, and that gives me minus 0.102 meters. So our position after, so x and y, after 2.00 times 10 to the minus 7 seconds is going to be equal to the coordinates we just found. So we said it was 0.4 in the x direction and minus 0.102 in the y direction. And of course, that's in meters. So that's our answer for B. And then for C, they're asking what will be its velocity at this time. Now, for this part of the question, we just use our velocity equation. So we said that the velocity, let's do x first, right? Because that'll be easy. So in the x direction, we know that the speed at any time, maybe v of x, is equal to v naught x, right? Because the speed doesn't change. There is no acceleration. And we were given that initial acceleration, which is 2.00 times 10 to the 6 meters per second. And then in the y direction, it's a bit more complicated, but we know that vy is equal to v0y plus the acceleration in the y multiplied by time. So we can plug in all these numbers, right? We know everything here. We know this value. We calculated this value, and we were given this value. So everything can be plugged in. So Vy is equal to the initial speed, 3.00 times 10 to the 6. Acceleration, we calculated to be minus 3.51 times 10 to the, what was it? It was 10 to the 13. And then time, they're asking us after 2 times 10 to the minus 7 seconds. So we plug this in, we can calculate it, and this gives us minus 4.02 times 10 to the 6 meters per second. So our speed, our velocity, maybe I should write v is equal to 2.00 times 10 to the 6 minus 4.02 times 10 to the 6, and this is in meters per second, right? So we have the x-coordinate and the y-coordinate of our speed. Now, usually, when we ask for the velocity, we like it to be in the form of the magnitude and the direction. So we can just transfer it like quickly. It's really not that difficult. It's quite, and it'll save you points in case your professor is expecting to have it in this form. So the magnitude of the velocity is given by, I'll write down the formula quickly. I mean, it's just Pythagorean theorem, right? If you think of having a speed like that, let's say, well, its x component makes up the bottom half of a triangle. The side of the triangle represents the y portion. So the length here, which is what we're going for, so that is equal to squared, is equal to a squared plus b squared. Or if you solve for the magnitude, you get the square root of a squared plus b squared, like that. So that's what I did to get that formula. And then if I'm trying to find the angle here, I know that I can use my trig identities to say that tan of theta is going to be equal to the opposite side divided by the adjacent side. So b over a, or in other words, theta will be equal to the arctangent of b over a. So let's use this equation. I'm not going to write it down, but I'll just calculate it. So it's 4.49 times 10 to the 6 meters per second. And then if we look at our angle, we'll get arctangent of minus 4.02 times 10 to the 6, and then 2.00 times 10 to the 6. 10 to the 6 will cancel out, so we'll just get this. So minus 4.02 divided by 2, arctangent of that, and that gives us minus 1.11 radians. But I think degrees will be simpler, so I'll just convert quickly. So it gives me minus 63.55 degrees. Or you could write it as, of course, 296 degrees, whatever you prefer. So that's ABC. This is a bit of a longer question, but at the end of the day, it's just pretty much exactly the same as mechanics for these questions. We just have this new equation here that we've been using, which is F is equal to QE and F is equal to MA, and then we use that to derive QE is equal to MA. But aside from that, everything else is pretty much exactly the same, and you'd approach this problem the same way you would any other projectile question. Okay, so let's do example 3. So, example 3. Consider the plates below. Assume the beam of electron enters the plate with initial speed v0 equals 4.0 times 10 to the 6 meters per second at an angle of 35 degrees. If the uniform vertical electric field is E equals 3.0 times 10 to the 3 meters per coulomb, how much time did the electrons spend between the plates? And then B, at what horizontal distance do the electrons strike the plate? And then we provide you with this pretty helpful illustration. So I guess plate 1, plate 2, and then I know that the distance here is equal to B, and my electron starts here and has some initial speed v0 at an angle of theta. I also know that this length here is L, and then that the electric field is moving upwards like that. So this is the E field, and then the trajectory will look something like that. Parabolic motion, and then of course this is the positive plate, and this is the negative plate. Okay. So, for example 3, again, very similar to a mechanics problem, and we can just approach it in the same way. So for question A, they're asking us how much time did the electrons spend between the plates? So to answer that question, we can sort of ask ourselves, at what point did it begin traveling through the plates, and at what time did it end its displacement through the plates? So first of all, it starts at one end of the plate, right, at a specific given speed, at a given angle, and we know the electric field. But it starts at one side of the plate, and the motion ends once it strikes the lower plate, which is what they're telling us in the second question, so we can use that, right? So its motion ends after it strikes the second plate. So we can use that to solve. So what we're looking for here, really, is the time it will take us to travel the length of the lower plate. So let's calculate that. Okay. So the first thing we might want to do is convert the velocity into two components, as I was talking about before. So they give us the initial speed in a bit of an inconvenient way, so we can split it up. So Vx is going to be equal to V0 cos theta, and then Vy is going to be equal to V0 sine theta. So V0 is 4.0 times 10 to the 6. And then cos, and the angle at which it's leaving is 35 degrees. And then for this one, it's going to be the same thing, but with cos. This one with sine. That gives us 3.28 times 10 to the 6 meters per second. And then we can do this one, 2.29 times 10 to the 6 meters per second. So now we have our two components. So this is Vx, and this is Vy that we found. Now, what they're asking is how much time did the electrons spend between the plates? So at this point, I know the value of E, I know the value of V0. Do I know anything else? And I know nothing else. So I somehow need to come up with a time from these values. At this point, we need to find a new relationship, right? Because all we have is the speed and the electric field, and I want to know time. And in my equations where I have time, I have acceleration, time, initial speed. I have a bunch of things that I don't really know. So I need to use a different relationship to come up with some new variable, right? So I can use the same equation that we've been using for the past few examples. F is equal to ma, which is also equal to, we can do the exact same thing, QE. Then we can do the exact same thing where we solve for A. So that's the equation we get. And then, of course, we have a beam of electrons, right? So the charge is going to be the fundamental charge of an electron. So negative 1.6 times 10 to the minus 19. And then we have the electric field, which is given in the problem, which is 3.0 times 10 to the 3. And then we divide by the mass of the electron, which is 9.11. And we pop this in a calculator, and it should give us minus 5.27 times 10 to the 14 meters per second squared. Of course, it's negative, which again makes sense because the particle is experiencing an acceleration towards the bottom in the y direction. Okay, so that's our acceleration. So now we have a bit more information. We have the initial speed, we have the acceleration, and we have the mass, and we're looking for the time. So we can use this equation here. So we know that the difference in y is equal to 1 over 2, or I guess I'll write the difference in y is equal to the initial speed in y, of course, plus a half times the acceleration times the time spent divided by 2. So we don't have a value for d, so we're just going to have to run with, I guess, delta y. So for now, because we don't have a value for d, we can say that delta y is equal to d, I suppose. So we want to find t, but we're not given a specific value for d, so we just have to imagine that delta y encompasses d, so it's like y is 0, or it's just equal to d, actually. So we'd get d equals all of this, v0y, which we know, plus 1 over 2a. So we know this value, we know this value, and we're looking for t. So this gives us a quadratic, so you'd solve minus d plus v0y, and that would give you your sort of c term, of the quadratic. And then you'd have your a term of the quadratic here. And so you would do this, and then you would solve for t if you were given a value of d. And then that would be how long the electrons spend between the plates. Now, for question B, they're asking us at what horizontal distance will the electrons strike the plate? And again, it's really not that bad, because when they ask for horizontal things, it's easy because there's no acceleration. So we can just use our simple equation, which is delta x is equal to v0, or the speed at any point, which never changes in the x direction, multiplied by the time. And we had solved for the time over here, so we could just use that same value that you would have got there, multiply it by the initial speed in the x, which we calculated at the very beginning over here, and then you would plug those two things in, and then you would get a value for delta x, and that would be how long it's traveled before it strikes the lower plate. Okay, so let's talk about torque. So when it comes to torque, we're mainly going to talk about torque on electric dipoles in this class. So if an electric body is placed in a given field, the the body doesn't really experience any force, right? Because it's neutral. So, however, even if it experiences no net force, the fact that the body contains both positive and negative charges means that it might feel torque. And if the electric field is uniform, um, the net force is zero, but we might see some sort of rotation due to that torque. So let's write that down. So, then if the electric field is uniform, so overall, the body will experience no net force. So, what we normally consider is the case of an electric dipole. So, let me define that. An electric dipole, which is really just a pair of point charges with equal magnitude and opposite signs. So, pair of point charges and opposite signs. So let me illustrate what we've been talking about, just so we get kind of a better idea of what's going on. So first of all, let's imagine we have some object with a length, right? Like this. Let's say it has a length, I don't know, L. And because and we know that this body is neutral, right? So overall it's neutral. However, even if it is neutral, it still contains positive and negative charges, right? And because it's neutral, we know that the number of those charges are going to be equal. So let's say it has, you know, this is just a random number, but let's say 3 of each. 3 positive charges and then 3 equal negative charges, right? So normally, okay, and then let's draw the E field, right? Just to be clear. Let's draw it in this direction here. So this is the E field. So even if the body experiences no net force, and we can even understand why that is, right? Why does it experience no net force? Well, these positive charges each are experiencing a force like that, right? So we have three forces moving in that direction. But we also have three forces moving in this direction. And these forces, because those charges are of equal magnitude, are all going to cancel out. So if I was to draw this, a free body diagram of the situation, it's all the same object, right? So I would have three forces in this direction and three forces in that direction. So the net force is equal to 0. So F, the sum of all the forces in X, is equal to 0. The sum of all the forces in Y, which, we don't even have any because the field is horizontal, is also equal to 0. So the net force in this situation is 0. However, because the charges are on opposite sides of the object and there is a length between them, there is a torque that is going to be exerted on the object. So these negative charges are going to be pulled in this direction, right, against the field lines, and the positive charges are going to be pulled in this direction. So even though the net force is 0, the object is still going to tend to rotate. And we say that it tends to rotate. It tends to rotate towards the dipole, and we define the dipole as moving like that with P. So I can write it down. So the force on the two charges both have a magnitude of QE, but their directions are opposite, and they add to 0. So, and maybe I'll write a note about the rotation. So this tends to rotate. So there is a net torque. Okay. So let's quantify the torque now. So first of all, the force on one side is going to be equal to the force on the other side. Their magnitudes, right? Of course, they're of opposite signs, but their magnitude will be the same, which is equal to QE. And then the torque is going to be equal to exactly what we saw in mechanics. So the perpendicular force to the object multiplied by how far it is from the point of rotation. So this is, the definition of torque. But then we have that if we take the point of rotation to be the middle of the object, we could say that it's equal to F1, let's say we're talking about the torque on one side, F1 times sine theta. So that, of course, represents the horizontal component, right? If you have the torque like that, point of rotation, you have an angle here. The horizontal component, or the component that is perpendicular to the length, so this component here can be calculated with sine theta. So F1 sine theta multiplied by how far we are which we said is halfway across the object, so it's going to be L divided by 2, like that. Now, of course, the same thing can be said for F2, right? So torque 1 is that, and then torque 2, we can just write like this. F2 sine theta L divided by 2. So, if we calculate the net torque, so torque net, we get that it's equal to F1 sine theta L over 2 plus F2 sine theta L over 2. But of course, F1 is equal to F2, so we can simplify this equation. Let's call them both F. To torque net is equal to F sine, we could, and then, L over 2 plus L over 2 is just L. So you get FL sine theta when we add them both up. And now we're going to define what we call the electric dipole moment as being P is equal to QL. So I'll write that. This is the electric dipole moment. And then what else could we do? We could also say that F is equal to QE. So we could substitute that as well if we wanted. So QEL sine theta. And then we could change that again, right, now that we defined P, so that torque net would be equal to PE sine theta, or that the torque net is equal to the cross product of P and E. So, this leads us, so from these equations, we can conclude three things. So first of all, if the electric field is perpendicular to the dipole moment, so is perpendicular to is perpendicular to P, we get that the torque is the greatest, right? Just because it's a cross product. And the same thing, so I'll write all of these out. So if E is parallel to P, then the torque is going to be 0. And then if E is anti-parallel, it's obviously also going to be 0. So in all of these scenarios, this is going to be what we get. So in other words, this is when theta is equal to 90 degrees. This is when theta is equal to 0. This is when theta is equal to 108 degrees. So we can do an example. A certain, there we go. A certain electric dipole consists of an electron and a proton, which are 0.400 nanometers apart, with the proton at a position angle (35 degrees) from the electron. And then we know, and then they also tell us that it's in an electric field that's uniform, of course. That's what we're considering in this case. So it is in an electric field that is 3,000 Newton coulombs. And then they're asking you, A, what is the electric dipole moment vector? And then B, they're asking you, what is the torque vector on the dipole? Torque vector on the dipole. And A, they're asking us what is the electric dipole moment vector. So we defined earlier the electric dipole moment to be Q times L. So we said that P, where is it? It was here. The P is equal to Q times L. So P is equal to Q times L. So in this case, we're looking at an electron and a proton, right? So the charge that we're dealing with here is 1.6 times 10 to the minus 19 for both the proton and the electron, right? So of course one of them is positive and negative, but that doesn't matter here. So P is equal to Q times L. So we can just plug in what we know. So first of all, we have that Q is equal to 1.60 times 10 to the minus 19 coulombs. L is equal to 0.4 nanometers, 0.400 nanometers. And here we have an angle, right? So the dipole consists of two components, right? Because it's a vector. So really, even though we have this, we have, in reality, P is equal to, so P has like an X component and a Y component, and that X component is going to be equal to this here at whatever angle we're talking about, and then the same thing goes for the Y direction, right? Because we're at an angle and we're not straight. So if, for example, we were feeling torque like that, the dipole would just be equal to QL in one of the directions, right? In X and Y, depending which way you look at it. But here, we're at an angle, so we need to consider, we need to use our trig functions. So for Px, we get P cos of theta, and then for Py, we get P sine of theta. So together, we get that P is equal to QL. So I guess we could calculate QL on its own. So 1.60 times 10 to the minus 19. And then L is 0.400. Nanometers is times 10 to the minus 9, so we can write like that. And that will give us, let's calculate that, 6.4 times 10 to the minus 29. There we go. And then here, we would get 6.4 times 10 to the minus 29 cos of 35 degrees. And then in the y direction, we'd get that same number, right? Times 10 to the minus 29. But now sine of 35 degrees. And so if we calculate this, we get that 6.4 times 10 to the minus 29 cos of 35 gives me 5.24 times 10 to the minus 29. And then for the y components, let's see what I get. 3.67 times 10 to the minus 29. So that is our dipole vector. All right, so not too bad for A. Okay, so for B now, they're asking us what is the torque vector on the dipole. Okay, so here we're going to have to use the cross product. So P, so I know, again, as I defined earlier, that the torque is the cross product of the dipole and the electric field, right? So I'm crossing one by the other. And so we just have to do that, right? So we just have to use sublinear and find the dot product. So we get this here, right? We can make our little table, and then P, of course, is 0, or is, let's say, has an x component, which is 5.24 times 10 to the minus 29, and then has a y component, which is 3.67 times 10 to the minus 29, and then the z component is 0. And now when it comes to the electric field, we can think of it as, to understand which direction it's moving, we can illustrate it kind of as follows, right? So imagine I had the dipole like that. That 35 degrees that we've been talking about would look like that, right? It would be from the horizontal. So the force, so let's say my E field is going like that, and that this side is negative, let's say. The forces that we'd be feeling were like that, and then like that, right? These are the forces. Of course, we don't really care about the forces, but those would be the forces. And so the E field here is moving in the positive I direction, or the positive X direction. So the only component it would have would be an X component that should be positive, that should represent the magnitude of the electric field, and it should have 0 0 y and 0 z, right? It shouldn't have any other components or any sort of value in its other components. And they tell us that the electric field is 3,000 newtons per coulomb. So we get that entire 3,000 in its I component. And its J component would be 0, and its K component would be 0. So we can, calculate the result here. So I'm going to get 0 times I minus J, just going to give us 0, right? And then I'm going to get a K, which is going to give me 0 minus 3,000 times 3.67 times 10 to the minus 29. So, that gives us minus 1.1 times 10 to the minus 25k. So it's actually going inside the plane. Okay, it's also worth noting that you could calculate this a much easier way. Instead of using the cross product, I just did it with a cross product, so you'd be able to do it in any scenario. But you could also use just, the normal formula, this here. Because you have all of these values, and then you could just plug everything in. But keep in mind that if the electric field were not moving, horizontally, you'd have a bit more difficulty. Okay, so let's do example 5. So a small straight bit of thread has a charge of right here 1.0 times 10 to the minus 14 coulombs at one end, and a charge of minus 1.0 times 10 to the minus 14 coulombs at the other. And then they tell us that the length of the thread is 2.0 millimeters. So A, they want to know the dipole moment. And then B, they want to know that they want to know what the torque is. So what is the torque on this thread if it is placed in an electric field of 6.0 times 10 to the 5 newtons per coulomb at right angles to the field. To the field. Okay. So let's do A first. So A, what is the dipole moment? So we define the dipole moment again. So it's equal to Q times E, right? We're just going to do exactly what Q times L. We're just going to do exactly what we did above. I know this, right? I know this to be true. So I'll just compute QL for convenience. So 1.60 times 10 to the minus 19. And then they tell me that the length of this is 2 millimeters, so 2.0 times 10 to the minus 3. And then you compute this, so I'll do that on my calculator. Oh, sorry, this is not the fundamental charge here. This is 1.0 times 10 to the minus 14. So that gives me 2.0 times 10 to the minus 17. And of course, and also, if you're trying to give a direction, as when we defined it over here, let's see where I did it initially. The dipole goes from the negative to the positive. So from here, if you want to write a direction here, you could write under from the negative charge to the positive charge. Okay. There we go. And of course, because we're at theta equals 90, this is going to give me 1, and this here is going to give me 0, right? So I'm really going to get, this is only happening in the y direction, right? Because if theta is equal to 0, I have this, right? So that's the direction of my dipole. So it's a lot simpler than it was in the last question where we had something like that. So theta was like that, so our dipole had an angle, right? And that's why we gave it both an x component and then a y component. So yeah, here only the y component exists, and the x component is equal to 0. Okay, so in question B, they're asking what is the torque on this thread if it is placed in an electric field of 6 times 10 to the 5 newtons per coulomb at right angles to the field. So, again, let's think about our torque, right? So we know two things. We know that our torque is equal to the cross product between the electric dipole moment and the electric field. And we also know that torque is equal to this here. So, we can calculate this using this guy here, right? So the dipole, we just calculated that to be 2.0 times 10 to the minus 17. And then the electric field is given to be 6.0 times 10 to the 5 newtons per coulomb. And then, of course, we have the sine of 90 degrees, which is just equal to 1. So we can do that. Minus 1.2 times 10 to the minus 11 Newton meters. And in other words, if you were to note, you could say that this is the maximum torque. Because, as we said earlier, let's see, we have this scenario right here. So the E field is perpendicular to the dipole moment, so we're getting the maximum amount of torque possible. So, in other words, we have torque, which is perpendicular to the field, and that amount of torque is the most it could possibly be. Okay, so, one more example. And the ball attains equilibrium at an angle of 35 degrees with the vertical. So the mass of the ball is given. So the mass of the ball is 3.0 times 10 to the minus 5 kilograms, and the charge is 4.0 times 10 to the minus 7 coulombs. They're asking you to find the magnitude of E. And they give you this illustration here. They tell you that's 35 degrees. and then it's telling you that the E field is coming in like that. Okay, so to answer this question, first of all, we can kind of think of what's happening, right? So the ball has a charge, which is given, and it's equal to 4 times 10 to the minus 7 coulombs. So first of all, we could note that that charge is positive, right? Which, even if they didn't tell us the sign, we could have also deduced because it's being pushed in the direction of the electric field lines, which is, of course, the direction in which a positive charge feels the force. So it must be positive. So we know that we have a positively charged ball, right? And if we think about all the forces acting on the ball at that point, there's gravity, right? And then there's tension. So maybe I could draw this in an FBD just to demonstrate. So if I draw the free body diagram, I have also if that's 35, then that angle should be 90 minus 35. So it should be 55. So I should have an angle of 55 degrees here, and I'm feeling tension in that direction, and then I'm feeling gravity in this direction. So this is Fg. Let's call this tension. And yet I'm kept away from the wall. I'm not touching the wall. So there must be another force in this direction, which is, of course, the electric force, right? Which is due to the E field. So that is how we get the value of E out of this scenario, right? So if we look at all the forces, let's begin by looking at all the forces in the x direction, right? Because it will be more clear. So I have this force here, right, which is the electric force, actually, I should write. But we know now that the electric force is equal to the electric force, the E field. All right, hold on a second. I think I defined it like this before. F over Q. So if I want to solve for F, I get that F is equal to E times Q. So in my equation of force, which says that all the forces in X should be equal to 0 because we're at equilibrium, and this is the equation that you get from mechanics, right? You would get that EQ minus, and then I get the tension force, and this is 35, right? So I want the X component of that, so it'd be sine of 35 must be equal to 0. So here, let's think about what I know. I mean, sine 35 is a number. I know Q, right, because it's given. I don't know E. I'm actually looking for E, so that's pretty convenient. Okay, so let's consider what's happening in Y right now. So in Y, what do I have? Well, I have gravity, first of all. So, or I guess first of all, we could write that all the forces are equal to 0. And then we have gravity. And then we have tension. So for the tension, I'm going to get T cos of 35 minus gravity, which is going to be equal to mg, is equal to 0. But notice now that, well, I know the mass of the ball. It's given. Gravity, or g, is a constant, it's 9.81, and cos of 35 is a number. So at this point, I'm able to solve for the value of t. So I can get that t is equal to mg divided by cos of 35. And now I can go back to my initial equation, and I can replace t. So let's do that. So I have that EQ is my EQ minus t sine of 35 is equal to 0. So I replace t. So I can rewrite this a little bit so that it's nicer. mg tan of 35. And then I could simply solve for E. mg tan of 35 divided by Q equals E. And there we go. So now we solved our question. So let's plug in our values. So they tell us that the mass of the ball is 3.0 times 10 to the minus 5 kilograms. Or I won't write the kilograms. But we know that, 9.81, then tan of 35. And then they tell us that the charge of the ball is 4.0 times 10 to the minus 7. So we can solve now. So I'm just going to punch this in my calculator. So I get that the electric field is equal to 515.18 newtons per coulomb. And keep in mind that this is in the positive x direction, right? As is shown in the illustration above here. So that's that. That is the last example for the for this chapter. So let's move on to the next chapter. Electrostatic potential and energy. Okay. So quickly to recap, first of all, we talked about the force, which is equal to K times Q1, Q2 over R squared. Then we talked about E, which is equal to K times Q over R squared. And then we said that because of that, we have F, or E, is equal to F divided by Q. That's what we did so far. But now we're going to be talking about the electric potential of a positive point charge, which we're going to denote as V. So let's write that down. So the electric potential of a positive point charge V. So let's draw this. So if I have a positive point charge, I'm going to define V as being as like this. There we go. If I'm trying to draw V, it would look something like that, where the positive charge in the middle is a point charge. So I know a few things, right? I'm going to define a few things. So first of all, moving with the E field decreases the electric potential. Okay, and then obviously moving against it will increase the E field, so or will increase the potential. So moving against will increase it. Okay. What else could we say? We could, I guess, I'll quantify it now as well. So in general, V is equal to K times Q over R, and okay, this is going to be for the units are going to be in joules per coulomb, and then also it's worth noting that this is only, or it can only be used for point charges. And so because like if we were to graph now what this would look like as we move away or towards a point charge, it would look like this. So if we were to graph the potential as a function of the distance, we get something like that. So what we see here is that the potential of a positive charge is positive, but it decreases in inverse proportion to the distance. So what that means is that the potential is inversely proportional to the distance, or to r, or v is proportional to 1 over r. And so the same, or I guess the opposite, can be said if we have a negative charge. So now if I have a negative point charge, let's say something like that, I could do the same thing. So it would look like this. So we get pretty much the opposite rules of what I was explaining before. So moving with the E field decreases the electric potential. And here it's worth noting that I say decreases, but here the magnitude is increasing, right? Because so V is equal to minus K Q R. So, I mean, I said it was the opposite, but when I say the opposite, I'm talking about the magnitude. In terms of the rules, they're still the same, right? So moving with the E field still decreases the electric potential. That's because I have a negative sign here. So if I just consider the absolute value of this, I take the absolute value on both sides, then this number is actually getting bigger as r gets smaller, right? It's just that because I have a negative sign in front of it, really I'm getting a more negative number, which means technically I'm getting smaller. So it's still true that moving with the electric field decreases the electric potential. So moving with the E field decreases the electric potential. And then, of course, moving against the E field increases it. So, V, maybe I'll do it over here. As we go inwards, V decreases. I'll put a, sort of quotation marks around it just to show decreases, meaning the value gets lower and lower. Decreases as you move inward. And then, of course, V increases. And then when I say increases, I mean that negative value gets less and less negative, so it gets closer and closer to zero, but from the negative side, right? So V increases as you move outwards. And so if I were to plot what I plotted above here, so the potential as a function of the distance, I would get the opposite. So get something like that. Actually, my arrow would be still towards the top here, like that. So potential here, R here, I would get a line that looks like this. And so we get a slow and gradual, quote unquote, increase in the potential towards zero. Okay, so now we're going to talk about sort of potential and energy. So I'll create a new section for that. Okay, so when we move a point charge from one point to the next within an electric field, work must be done. And that is because there is a change in the potential energy, right? Because imagine I have this equation, right? And I'm using it. If my R changes, so let's say I have R1 and R2, I calculate V at two different points. Well, I'm going to get two different values of V, right? And V we defined as being potential. And if there is a change in potential, well, there must have been work that is done. Well, there must be a change in energy. So we can say that work is done in moving a point charge. I'll call it plus Q from Y1 to Y2. And I'll draw that in a second. So is done in moving a point charge from Y1 to Y2. So this is minus Q. This is plus Q. And then we would have our E field going something like that. And then let's say Y1 is over here. And then Y2 would be, I don't know, somewhere over here. So we have a translation, a vertical translation from Y1 to Y2. And we would have a decrease in potential energy. Because here, we're so close to the positive plate, right? Our distance R1, so this is R1, right? But then this would be R2. R1 is significantly smaller than R2, and because we said that V is proportional to 1 over R, if R1 is smaller, well then V1 will be smaller. So V1 will be larger than V2. So what that means is the potential energy decreases in proportion to the distance y. So the potential energy decreases in proportion to the distance y. And moreover, the electric force, it does work, which we can compute as FV, right? That's the formula for work. But here it's going to be F delta Y as Q moves from Y1 to Y2. So the electric force does work. W equals F delta Y as Q moves from Y1 to Y2. Okay, and from this we can sort of derive quite a few equations. So we call the electric force that a static distribution of charges exerts on a point charge a conservative force. So the work, and we can define it and quantify it as follows. So the work done by this constant force F is equal to QE is, so we defined it earlier, F is equal to, W is equal to F delta Y. So F is equal to, or W is equal to F times Y2 minus Y1. So we could also say then that the potential energy is equal to, or actually what we can do is we can replace F by QE or EQ. So let's call that like that. U, so the potential energy, right, is equal to Q E Y, where Y is, we're kind of replacing Y here by delta Y. Same thing here. So V, so that's U, make that a bit clearer, that's U, and this is V, is equal to EY. So in other words, U must be equal to QV. And this here, U is equal to QEY, this will be the potential energy. There we go. And then, of course, E is the electric field. And then Q is going to be the charge in coulombs. So we can illustrate this now. So the charge, so okay, well, let me begin by writing it, and then I'll illustrate it. So the charge Q moves in the direction of E. E does positive work. Then the potential decreases with height. And then if we have the opposite scenario, so if Q moves opposite of E, then E is doing negative work and U is increasing. So if Q moves away, or I'll say opposite of E, then E is doing negative work. And then U is increasing. And then, you could also note that the inverse is true if we have a negative charge. So, let's show that. So, if I have, for example, my y-axis like that, And then I have an electric field that's moving upwards. So let's draw it like that. And if I have a particle here versus here, so let's say that's that same particle, at the lower point, it's going to have a relatively high potential energy, or a high potential energy relative to that second point. So it's going to have a high potential energy, and here it will have a low potential energy. And you can sort of reason through why the two last points I made are true, but if you think about it, if Q is moving in the direction of E, that means that, first of all, what does that mean? That means that Q is moving along the electric field lines, right? So Q, let's say, would be moving like that, right? So that means that the positive charge is moving in the direction along which it feels a force. And if that's true, well then it's getting farther and farther away from the positive plate, right? So U is decreasing, right? And then if U is decreasing, right, it's feeling less and less energy from that positive plate. Well, what that means is E is doing positive work on it, right? The field is the thing pushing it in that direction. So that's that. We can now kind of translate this a little bit to what we know already about energy, because we know that energy, or total energy, is equal to the kinetic energy plus the potential energy. And now we've defined a new sort of potential energy, so we can combine these in what's called the work energy theorem. So let's write it down, the work energy theorem. And it states that so the work is equal to the change in kinetic energy, or in other words, the work is equal to the negative of the change in potential energy, where delta K is equal to K2 minus K1, and then of course delta U is going to be equal to U1 minus U2. Remember, it's U1 minus U2, not U2 minus U1. So, and then by conservation of energy, we have the following. So, conservation of energy, E, we can say that E is equal to K plus U, and K, mechanics, I know is 1 over 2 mv squared. Then we just defined U as being Q is equal to, U is equal to QEY. And we know that just because we have conservation of energy, the sum of both of these energies must always be constant, right? This value here specifically might go down, but then this value here will go up to compensate, right? Because their sum will always be equal. So their sum is constant. And what we get then is that, or I guess this is just another way of stating the conservation of energy, but K1 plus U1 is equal to K2 plus U2. And then, of course, we can be more specific, and we can define all of our variables here. So E is going to be the total mechanical energy. K is going to be our kinetic energy. And then U is going to be our potential energy. So we can describe this. So when a positive charged particle moves from higher to lower potential energy, work is done, or the work done is going to be positive, and the U will decrease. So when a positive charged particle higher to lower potential energy work is the work done is positive. And we have that U is decreasing. And then conversely, if a positive charge moves from lower to higher potential energy, the work done is going to be negative and U increases. And again, we can think of this, it makes sense because if we're moving against the E field, we have to produce some sort of force, right? We need some external force because the E field is pushing against us. It's like walking against the current, right? Or swimming against the current. So when a positive charge particle moves from lower to higher potential, work the work done is negative and U increases. So let's talk about the electric potential of a point charge. So first of all, as we said earlier, we have the formula. I'll do it in black here. V is equal to K times Q divided by R. And of course, this is for point charges only. And then we have, we can say that the potential of a point charge is the same as a few things. So first of all, it's always equal to, if we had an electric potential outside a solid charged sphere, it's the same as a hollow charged spherical shell, or sort of any charge with spherical symmetry. So, and the reason you need to know this, or the reason I'm saying this, is just because it might come up in like a multiple choice question or something. So, it's just you just need to know that. So, the same as. So again, this can mostly just be memorized. Okay, so now let's consider how the electric potential behaves in the same scenario that we were talking about before. So since the beginning, or I guess for a few lectures, we've been talking about um, two charged plates with a constant or a uniform electric field between them. So how does the E field, or how does the electric potential behave in that scenario? So the scenario we had, first of all, was that, so we had the electric potential. So we had our battery here, right? And then we had, of course, one of these was positive, the other one was negative, and then this plate was positive, this plate was negative, and then what we have is that the E field is going to go like that. And so what we have is that the potential is going to be equal to the E field multiplied by the distance, or I guess it's equivalent to saying EY, right? Because we could kind of call this thing Y, the distance between both of them. So, in other words, we can come up, and then we, with this equation, and because we're in between two plates with a constant electric field, we can come up with the following equation. So, we know that U is equal to Q EY, and then also we know that V is equal to EY, right, from this scenario right here. So, the work done so in moving Q from A to B, right? So let's say I have some random point A here, right? And I want to move to point B. The work it will take me to move from point A to B, we can calculate using these equations, right? So the work, let's call it A towards B, we could say is UA minus UB. Remember, it's always U1 minus U2, right? And then we can factor out Q, right? Because I skipped a step here, but U is equal to Q EY, right? And QE is also just equal to, or EY is equal to V. So U is equal to QV. And then I'm factoring out the Q. So I'm just getting V inside the parentheses. And then we can define VAB as being VA minus VB, such that VA, or the work done from A to B, is going to equal to QVAB. So now if we consider this scenario at infinity, right? And when I say infinity, that is to say, if I move very, very far away, meaning R is extremely, extremely large, right? It's like, that's kind of analogous to taking the limit, right? Like, imagine I do this. V is equal to K, Q over R, right? This is equal to 0. That's kind of what I'm saying here. If, right, and this is also just V, right? So the potential at 0, and of course U at when, sorry, not at 0, when we go to infinity, when r goes to infinity, is equal to 0, right? Because the force and the field and the potential are going to be so low that we just call it 0, right? That's the idea, is just a limit, really. So we can write that down because that's important. And the reason why that's important is because in later problems, we might say, what is like you might need to know the difference in potential between a point that's infinitely far away and near your electric field, right? Because when you're really, really far away, you're just going to be able to say that whatever you're talking about, let's say it's potential, is practically 0. But when you bring it all the way into the field, it's equal to, I don't know, something that's not 0. So you'll be able to say that the difference, VA minus VB, is just equal to one of the two, because the other one is just equal to 0 because it's so far away. So that's why this is useful. So I'm going to write that in red, actually, because it's very important. So the electric potential and potential energy are said to be 0. So V equals 0 and U equals 0. And this is, of course, at infinity only. Okay. So, I guess we could start on a few examples. So, first of all, example 1. When a positive charge moves in the direction of the electric field, comma, A, the field does positive work on it, and the potential energy increases. That's option A. Option B is the field does positive work and the potential energy decreases. Option C is that the field does negative on it and the potential energy increases. And then option D is that the field does negative work on it and the potential energy decreases. So if I was to draw this out, I would have something like that. So I would have the E field, which is moving in this direction, and then I would have a positive charge like that moving in that direction, right? With a charge of plus Q, let's say. And so they're asking, if a positive charge moves in the direction of the electric field, what's happening really? So because I'm moving in the direction of the electric field with a positive charge, I'm moving in the direction that I'm experiencing the force, right? Because of course the E field lines point in the direction that a positive charge will experience that force. So I'm moving in the direction that I want to move. So the field is doing positive work on the positive charge. And then naturally, as I move away from the source of that E field, right? Let's say the positive plate, if we were in between positive and negative plates, well, my potential energy must decrease. So in other words, I'm doing positive work and my potential energy decreases. So the answer is going to be positive work, potential energy decrease. The answer would be B then. There you go.